Hello, welcome back. In this video, I'm going to discuss the items that you need to pay attention to when you prepare for an SEM study. The first item is about model specification. Remember, the model you proposed should be theory-driven. The variables you decide to include and their relationships need to be supported with theoretical and/or empirical evidence. Also, it is critical for you not to leave out any important causal variables. For example, in a study, you would like to examine what factors has causal impact on the math performance of middle school students. The primary variable you're interested in is the time, the number of hours students spend doing math work after school. You included variables that measure teachers' effectiveness, but you failed to include variables that measures students' math self-efficacy, which happen to be one of the critical variables that impact student math performance according to the majority of the literature. This is an example of specification error. You do not have causal closure by leaving out some critical causal variables from the model. The second item is about the directionality of variable relationships. Once you have all your variables, you know the relationships, it's better to present your model in a diagram, the conceptual diagram. This is an example of a conceptual diagram. You would like to see clear directions in the variable relationships that you specified. A model like this is called a recursive model. There is another type of models that's called non-recursive model, in which you see the causal relationship between two variables is not clear. It's bidirectional. There are often mathematical problems and identification issues associated with non-recursive models. So I do not encourage you to include this non-recursive type of relationship in your model, and it's not going to be covered in our course. The third item is about latent factors. If you have latent factors in your model, you want to make sure you measure them with instruments that have good reliability and validity. In many cases, you can find published instruments that measures the latent factors you're interested in. In case those published instruments do not meet your requirement or your intention very well, you can develop your own instrument, but that requires a lot of work. In either case, you are highly encouraged to collect pilot data on your instrument and modify the items if needed before you start your real data collection. The fourth item is about sample size. You go to different sources, they have different rules for you. Some tell you your sample size cannot go lower than 200. SEM is a large sample technique. I would like you to follow this rule of thumb when you design your own study. For every parameter you need to estimate, you need to have at least 20 observations. So if you have 10 parameters in your model, you need a sample size of 200 or larger. Just to make it clear, the parameters are those unknown values in your model that you need to estimate in order to present your final structural model. And they include things like past coefficients, variances, and covariances, etc. Let's see, you have finished your literature review, and you presented your conceptual model, you identified the instrument, and collect the data. It's time for you to take time and patience for data preparation. First, it's very likely that you are going to have some missing data. The question is, how are you going to handle those missing data? Yes, you can delete the cases with missing data if your sample is sufficiently large. However, if your sample is small and you cannot afford deleting all the cases with missing data, you have to think about some way to impute those missing data. How to impute missing data could be a lecture all by itself. Since we don't have time to go into too much details, I just gave you a few examples here. Mean replacement is a common approach. For example, there are 5 survey items measuring the same construct. One of the respondents answered 4 of them, but missed 1. You can find the average of the 4 items he answered and use that mean value to replace the missing value on item 5. In some studies, regression is used to impute missing data. For example, in a study, there are variables measuring people's annual income and years of education. If some respondent didn't report their annual income, you can construct a regression equation based on those observations that do not have missing data and plug in the years of education into that equation to predict or estimate the income level of those who did not report that information. The most popular imputation method now is called multiple imputation. It requires the missing data are missing at random or sometimes missing completely at random. I do not have time to talk about this in details, but if you're interested, I have a link for you. This is a good video for you to learn how to do that in SPSS. Regardless which imputation methods you decide to use, be sure to sufficiently justify your choice in writing when you write your final paper. Outliers are another issue you need to consider when you prepare your data. It's easy to identify univariate outlier. You just look at the distribution of a single variable and see if any of the cases has extremely high or low values. It is difficult to identify multivariate outliers. We learned in regression to use distance tests to identify those outliers. Here, I want to use bivariate outlier to show you how to handle outliers in 2 different ways. In this example, we have an outlier here. If this is the regression line, you can see that the outlier lies on this regression line. With or without this outlier, the bivariate relationships stay pretty stable. In this example, it's a different scenario. There are several outliers. When they are included in the analysis, the regression line was pulled toward them. When they are removed from the analysis, you can see this is a regression line. It goes much more flat. In other words, the outliers distorted the relationship, the true relationship between the 2 variables. And we do not want that to happen. So my suggestion for you is that you want to use visual tools or distance tests to identify those univariate and multivariate outliers. Then you want to run your analysis with the outliers and without the outliers. Compare the models resulted from the 2 different approaches. If they're pretty similar, you actually can keep those outliers in. That means they do not impact the model that much. If they really changed the model parameters, you would have to remove them from your analysis. The relative variances is the issue unique to SEM. Let me use this data set to explain what is relative variances. There are 4 variables in this data set. You can see that the range of the variable differ dramatically. For trust in government, the possible range is from 1 to 10. For feeling towards president, the possible range from 0 to 100. So this is 10 times higher. And you have 2 more variables that range somewhere from 8 to 24, 0 to 20. Those 2 are similar. So when you get the variances of the 4 variables, the variance of the second variable could be 100 times higher than the first variable. This dramatic differences in variable variances may cause problems in your analysis. And one solution is to do variable rate scaling. That is, you want to use linear transformation to change the values of variables that have extremely wide or extremely small ranges, so they can have comparable variances to other variables in the data set. For example, for the second variable, you want to divide all values by 4, so you could have a range from 0 to 25. For the first variable, you can time all the values by 2, then you would have a range from 2 to 20. After the rate scaling, the variances of all 4 variables will be quite comparable to each other. Since SEM is based on multiple regression, multicollinearity could be a problem too. This happens when you have 2 or more variables that are highly correlated with each other. When you have your data set, get a correlation table and see if any pair of variables have a correlation higher than 0.8. And you can run a multiple regression with your dependent variable to see if there's a problem with multicollinearity by checking the VIF. We want all VIF to have a value lower than 10. If there is a problem with multicollinearity, there are several possible solutions. First, out of those highly correlated variables, only keep the one that is most relevant to your dependent variable and remove the others. Second, use exploratory factor analysis to extract the underlying factor from those highly correlated variables and use the factor scores in the model to replace those variables. If those highly correlated variables share the same scales, you can actually combine them by finding their mean or their sum and use the mean or sum values to replace them in the analysis. In theory, SEM requires multivariate normality as its underlying assumption. We are going to talk about this more when we talk about the model estimation. For now, I want you to remember how to use skewness, kurtosis to evaluate univariate normality. In case you need some help, I have a video linked to the slides that shows you how to check univariate normality in SPSS. Some studies use data transformation when they do not meet assumption of normality. I actually do not encourage you to do that unless it's absolutely necessary. So I'm going to skip the discussion about data transformation for now. Remember, when you carry out analysis for a project, approximately 7% of the time is spent on data preparation. Only 30% is for the final analysis. So be patient. Spend the time, do a good preparation before you do the analysis.